Then I'll send you a link to listen the first part of the disconnection lecture that was recorded on a real lecture hall at the university. And then we'll come back here because it is very important. We'll shift into Polish, and the second part will be in Polish, basically to give some further hints and to repeat this part that will be available on the YouTube on that movie. Sorry, really sorry. So let's start with the screen. Yeah, it's here. And screen. Yes. Can you see my screen on your computers?
Yes, we can see.
So great. So we can now discuss parameters that are used for the characterization, for the description of synthesis results. I mean, we have yield for the description of work. So it is simply yield that we know from our third year course, simply the outcome of the experiment in our flask. So the experiment, what is important for the experiment is the experience of a guy who is performing the experiment in the lab, and then of course geometry and so on and so on. Then we have atom economy, we discussed last week, and then we start two parameters are called TLV or PEL or PEL. What are these parameters? Basically, it is something that relates to green chemistry, so threshold limit values or permissible exposure levels. It means that while experiment, we have some emissions, let's say, from the solvents or from the reactants or reagent. If we are in the lab, it's proper. It's apparently a more proper relation to the real experimented reactants, which is more appropriate for the description of in silico, or if we are writing something on the paper. So threshold limit value and permissible exposure levels are just, the values which are reference numbered, described from the institutions such as United States Occupational Safety and Health Administration, which simply can define what is a typical level of the exposure on this toxic chemical. And Environmental Protection Agency, it is another index. It's EPA index, toxicity weight, so-called toxicity weight. All of these indexes are basically similar. And we'll not discuss this in a very detailed way, because the most important thing is just to remember them. So we should be aware of this fact. So it is very important which way we are performing our experiment. That is even more important which way we will go in the industrial procedures for big lab experiments, which involves much larger exposure to the chemicals and toxic department of the reactions. And we can find it basically, but we should be aware of that. And let's say coming once more to the maleic acid, and we can see that if we say benzene row and butane row, the TLV indexes are almost the same, so about 4. It's simply we are summing the contribution from the different cancerogenic, for example, carcinogenic chemicals that are involved within the process. Once more, I would not like to concentrate focus on this very intensively. You can, for example, prepare in your project something like that, because basically chemists are not aware of that fact that we are to assess such things, that it is important for designing contemporary synthetic approaches in labs and in industry. The name is the most important here. Then we have the EPA, environmental index, and which is a little bit different due to the definitions. And we can see that EPA, if we say the butane road, is much better because we have this index here 0, and for benzene road it's over 100. What we are taking here is maximum toxicity of the reagent. And then we can describe the whole process of the production of maleic acid. Once more, these two rows, I mean the benzene process and butane process. I remind you that we discussed all of that in our recent lecture, so everybody can find the reference, the reaction, and so on. However, if we analyze very precisely the mechanism for that, we see that each process is much more complicated than a single reaction. So we need as much as here is 5 reactions to describe both processes. And you know, benzene conversion is about 95%, and butane conversion is 85%. And we can see now that conversion, what is the conversion? Is something, you know, that corresponds to the term yield. So it is what we are taking out of the experiment. And the yield is something more in the lab, you know. Conversion is between atomic economy, and benzene conversion is about 95%, and butane conversion is lower, 85%, and yield for benzene process is 70%, and butane is about 60%. And air to benzene ratio is about 66 moles, and similar to butane is about 62 mole. Temperature is lower in benzene process, is 375 centigrade, and butane is 400. Pressure in both cases 150 kilopascal. So basically the environmental data what we need to use in the reaction are similar in both reactions. So pressures, temperature are similar. All of that should take into account when we are designing synthetic approaches, because this simply defines our chemical, our technological process, our machines that we should use in that reaction for performing these reactions. Then we have here once more the economical data for the process, and we can see that the benzene process will cost us about $0.03 per mole of maleic acid, and and butane is about 0.02 dollar per mole, so it's cheaper. And raw material costs dominate total cost of the process. So it's often in chemistry that, I mean, chemicals is the highest cost of the whole process. And we do not have waste, of course, because it also costs us a lot of money to get rid of the waste, to design and to buy technology for that reason. So chemicals cost lower money for N-butane process. Then environmental impact analysis. So it is what we should also take into account while designing that process is that we, for 1 mole of maleic acid, is about 99% of maleic acid recovery from the reaction. And what I understand from here is this does not depend upon the process, so benzene or N-butane can be used, and regardless of what we are using, the results is basically similar. So we are obtaining pollution control 99%, and what we are obtaining is carbon dioxide, water, air traces of carbon oxide, maleic acid, and benzene. And we can also see here that, let's say, if we have this benzene is much worse than if we have N-butane, because benzene is highly cancerogenic. So we should avoid all the emission of benzene wherever and whenever it's possible. And then, so basically, this environmental impact analysis was previously present in our PLB or PEL analysis, so quantitative analysis. And then once even more detailed analysis, so benzene exciting reactor is about 0.07 mole of benzene per mole of maleic acid. Emission control, it means 7.2 mole of benzene, but it's 10 to minus 4, so it means it's that it's about millimole, yeah, level. And for N-butane, we also can have similar data. So we should have about 0.25 mole of N-butane per mole of maleic acid, and the pollution control means 2.53, 10 minus 3 moles of N-butane to mole of maleic acid. So even we can see that the maleic acid is one level higher because it's 10 to minus 3 versus 10 to minus 4 in benzene. Butane is less toxic than benzene. So once more, the environmental pollution and environmental pollution data, which is also currently very important for our analysis. When we have the carbon dioxide balance, and once more in benzene process, we have, let's say, about 4.6 mole of carbon dioxide per mole of maleic acid, and for N-butane is 2.7 mole of carbon dioxide, so it's lower. And we can see the data are not correlated, so we should analyze it in multidimensional way. So, for example, from one point of view, the benzene road is better. From the second point of view, the BK way is much better. Let's say the atom economy, for example, is more advantageous for the butane road. And then we have a typical emissions from a different, technological units. So reactor vents, distillation column vents, absorber units, stripping columns, sumps, decanters, dryers, cooling towers, and we have just emission factors. So emission factor on the right here, and it's a typical value. So while designing the process, we can easily calculate this or evaluate the importance of all of these processes for the whole synthetic procedure. And that, closes our part on the global effects, and we are now coming into the electrosynthetic analysis. I just start new recording here. Okay, new recording, and I'm closing this slide because we are coming now to the table. Okay, so can you see me? Hello, can you see me at the table now?
Yes, we can see.
So what we have a target molecule. A target molecule is what we would like to synthesize. And an example are molecules which last week I just sent you for the analysis, not even knowing that to find the reactant. Now, reactant, you will write table or on paper, and so it's just retrosynthetic analysis. So retrosynthetic analysis, or in Polish, analysis retrosynthetic, to find some Lego-like smaller blocks for synthesis, which will call us syntons. So syntons are not molecules. Syntons will be molecular entities. So basically, these will be nucleophiles or electrophiles capable of just reacting here the way of chemical reaction on this target molecule. So, and we will then follow this cycle as long as we find the molecule, and here will be just the reagent which will correspond to these molecular entities. So molecular entities will be model substances, will be just molecules, even molecules, something like molecules, because molecules just something that can have a form of substance. Here we have reagent substance. That's something that we can just take off. We can use in vitro to have a real target molecules when we are planning to. Of course, we'll have some further uh, possible procedures to uh, make the symptoms reactive, which we'll just try to learn in the next few lectures how to perform this typical operation to have the real reagent stuff. So basically what is important is that we should perform this connection within this target molecule. So find the smaller fragment to find symptoms capable of reaction as real reagents in a known or promisable reaction. Because we can use known reaction, we can use known reaction. So as these are that are recorded in databases, and then we can also use the reaction that we are designing. So for now, it will be all. And now I'll send you this link to hear my lecture on something that I would say is a symptom chemistry. Symptom chemistry, okay, this doesn't right. Symptom chemistry. Symptom chemistry. So I'm sending you in a moment, and then we'll meet. Let's say it's about 3/4. So let's meet at 11, and then I'll take you at Polish to just make conclusions and so on. So now I'm trying to find a second of technical break because someone has. So just a second, just a second. Okay, so a moment and I'll find the link for that. So have you got the link?
Yes, we received it.
Okay, so now everybody will just watch that movie and we are coming back here at 11, okay?
Okay,
Okay.
see you then.
See you again in a moment.